Look around you. The time on your phone, the price of a meal, the floor of a building, the percentage of battery remaining, and the distance to your destination all depend on numbers. Now imagine that every written digit disappears. You can still see 2 cups, several people, or a crowded street, but you have no symbols for 2, 7, or 100. Somewhere in the distant past, humans lived in exactly that world. They could recognize quantity, but they had not yet created the systems that let quantity be recorded, shared, and calculated. Imagine a small community watching animals return through a narrow opening at sunset. Something feels wrong. The group that returned looks smaller than the group that left, but nobody has a written list or a word for the exact total. How could anyone prove that one animal was missing? The solution does not require arithmetic. It begins with a simpler idea, matching every animal with something else. One animal could correspond to 1 finger, 1 pebble, 1 knot, or 1 mark. If an unmatched marker remained after the animals returned, the community would know that something had been lost. To understand the origin of counting, 4 different abilities must be separated. The first is sensing that one group is larger than another. The second is matching objects one by one to discover an exact quantity. The third is giving that quantity a spoken name. The fourth is representing it with a visible symbol. These abilities did not necessarily appear together. A person could recognize that one basket contained more food without knowing exactly how much more. Another person could count accurately with fingers while having no written numerals. The history of numbers is therefore not one invention, but several connected inventions. Long before humans developed formal counting, the brain could estimate quantity. Many animals can choose the larger food supply or avoid the larger group of rivals without counting each individual. Humans retain this approximate number sense. At a glance, we can usually tell whether a hillside holds 10 animals or 50, even when we cannot state the exact total. Accuracy falls as the quantities become closer. 10 and 20 are easy to distinguish, while 20 and 21 are not. This ancient ability helped living creatures make quick decisions, but estimation alone could not reliably track possessions, days, deaths, or missing community members. Very small quantities produce a different experience. Most people can recognize 1, 2, 3, or perhaps 4 objects almost immediately without consciously counting them. This rapid recognition is sometimes called subitizing. It may help explain why small quantities often receive special treatment in languages and social customs. 1 enemy, 2 enemies, and many enemies can demand different reactions even before exact number words exist. But this ability has a narrow range. A person cannot glance at 30 scattered stones and instantly know their exact number. To move beyond a few visible objects, the mind needs a repeatable sequence that assigns 1 marker to each item. Exact counting begins with 1-to-1 correspondence. Every object in a group must receive exactly 1 action, sound, body position, or physical marker. An animal passes through an opening, and 1 finger bends. A portion of food is distributed, and 1 pebble moves from 1 pile to another. A day ends, and 1 cut is added to a stick. The markers do not need to resemble what they represent. Their power comes from the rule connecting them. Once each object has been matched and no object is skipped or counted twice, the final set of markers preserves the exact size of the original group. This method transforms counting into a controlled performance. Suppose 12 gathered roots are placed on the ground. A person touches 1 root and moves 1 stone. The action is repeated until every root has been matched. The stones can then be carried elsewhere, compared with another pile, or used to distribute the roots fairly. The crucial breakthrough is not the stone itself, it is the realization that 1 collection can stand for another. That idea allows quantities to be compared even when the original objects are absent. It also creates the foundation for tallies, tokens, written numerals, and eventually calculation. The human hand offered an even more convenient counter. Fingers are always available, arranged in a stable order, and easy for other people to observe. A person can raise 1 finger for 1 object, add another with each new object, and close or reopen the hand when the sequence is finished. Finger counting also links quantity with movement and memory. A spoken sound can accompany each finger, allowing gestures and number words to reinforce one another. Archaeology rarely preserves these actions, so nobody can prove exactly when they began. Yet the worldwide importance of hands in counting suggests that they were among humanity's earliest numerical tools. Hands may also help explain why many number systems organize quantities around 5 or 10. One hand naturally creates a group of 5, two hands create 10. Adding the toes makes 20 possible. A community can count individual objects until one hand is complete, then treat that completed hand as a larger unit. The same process can be repeated with both hands or the whole body. This does not mean every base 5, base 10, or base 20 system had an identical origin. Cultures developed many different solutions. Still, the structure of the body offered visible groupings that could turn a long sequence into manageable bundles. Some societies extended counting beyond fingers and toes by turning the body into a mapped sequence. The count might begin at one little finger, move across the hand, continue to the wrist, elbow, shoulder, ear, eye, or nose, and then descend along the opposite side. Each body part represented a fixed position rather than a universal number symbol. To count, a person touched the positions in the established order. This allowed a larger exact quantity to be expressed without writing or loose objects. The system worked because members of the community shared the same sequence and knew where the count began and ended. Anthropological records from the Torres Strait and Papua New Guinea demonstrate how sophisticated body counting can become. Some documented sequences cross the body to represent 19 positions. The Oxetman system of Papua New Guinea traditionally uses 27 named body locations, beginning on one side and ending on the other. These systems are not living fossils from the Paleolithic, and they should not be treated as direct copies of prehistoric behavior. They reveal something more useful. The human body can support an exact, culturally taught counting system without written digits. Quantity becomes attached to an ordered path that other people can learn and repeat. Body counting also has serious limits. The result disappears when the gesture ends unless someone remembers it. Hands may be occupied by tools, food, or weapons. Large quantities require repeating the same sequence, which creates opportunities for mistakes. Two people must also agree on the order and meaning of each position. A traveler entering another community may find that familiar gestures mean something different. These limitations encouraged the use of external objects. Pebbles, shells, seeds, sticks, and cords could hold a count after the body stopped moving. Once quantity was stored outside the person, it could travel through space and survive through time. A small object can represent almost anything. One pebble may stand for one animal, one basket of grain, one completed task, or one day. The object has no numerical meaning by itself. Meaning comes from the rule established by its users. Pebbles are especially useful because they are portable, durable, and easily arranged into groups. Shells, seeds, or clay pieces can serve the same purpose. A counter can be added, removed, divided, or exchanged. The system allows exact comparison without number symbols. If two piles contain the same number of markers, the quantities they represent are equal, even when the original objects are nowhere nearby. Consider a cautious reconstruction rather than a known historical event. A keeper leaves a settlement with a group of animals and a pouch of stones. As each animal passes through a gate, one stone moves into a second pouch. When the animals return, the process is reversed. If every stone is matched, the group is complete. If one stone remains, at least one animal is missing. No archaeologist has uncovered this exact prehistoric scene, because loose stones rarely preserve their former purpose. Yet the procedure shows how one-to-one correspondence can solve a practical problem before spoken totals, written lists, or abstract arithmetic are available. Wood and fiber offered other ways to preserve information. A person could carve marks into a stick, thread objects onto a cord, or tie knots at remembered intervals. Such devices might track deliveries, journeys, days, or obligations. Their great archaeological problem is decay. Wood, plant fiber, leather, and ordinary string usually disappear unless preserved in unusually dry, frozen, or waterlogged conditions. As a result, the earliest surviving counting devices may not represent the earliest devices that existed. Archaeology favors bone, stone, and fired clay because those materials endure. The history we can recover is therefore only a fragment of the numerical experiments people probably attempted. Notching a durable surface created a major change. A gesture disappears, and a loose pebble can be separated from its meaning. A cut in bone or wood remains attached to the object. New cuts can be added over time, and the finished sequence can be carried, stored, or shown to someone else. This made marks useful as external memory. A series of notches might preserve a count, but it could also record stages of an activity, ownership, a story, or a ritual sequence. The appearance of repeated lines is therefore important, but repeated lines alone do not prove that exact numbers were being recorded. Archaeologists examine ancient marks at several levels. Under magnification, they study the shape, depth, angle, and microscopic surface of each groove. Similar cuts may indicate that the same tool and motion created them. Overlapping marks can reveal which cut came first. Changes in depth or direction may show that separate marking episodes occurred. Researchers also compare spacing, grouping, wear, and the archaeological context in which the object was found. Even this detailed work has limits. It may establish that marks were intentional, repeated, or added over time, but it rarely reveals the lost rule that connected each mark to a specific object or event. One provocative example comes from Les Pradelles in western France. A hyena bone associated with Neanderthal activity, roughly 60,000 years old, carries 9 similar incisions. Microscopic analysis suggests that the marks were made deliberately with a stone tool in a short period of activity. Their spacing does not resemble a perfectly planned decorative pattern. This has led Francesco De Ricco and other researchers to consider whether the incisions recorded a sequence of information. If that interpretation is correct, the object would show that Neanderthals could place ordered information outside the mind. It would not, however, reveal what the 9 marks represented. The uncertainty surrounding Les Pradelles is essential. 9 repeated cuts could correspond to 9 objects, but they could also help someone remember a message, identify ownership, structure a ritual, or mark progress through a task. Similar-looking marks have served non-numerical purposes in historically documented societies. No surviving voice explains the Neanderthal object, and no accompanying label identifies its meaning. The responsible conclusion is therefore limited. The marks appear intentional and organized. They may have stored information. A numerical reading is possible, but not proven. This distinction protects archaeology from turning an intriguing artifact into a certainty that the physical evidence cannot support. Far to the south, Border Cave lies near the border between South Africa and Eswatini. Archaeologists working there recovered a broken baboon fibula bearing 29 notches. The object, often called the Lebombo bone, comes from deposits roughly 42,000 years old. It is frequently described as the oldest known tally or even as a lunar calendar. Those labels go beyond what can be demonstrated. The number of surviving notches is clear, but the bone is broken, so the original sequence may have been longer. What survives is a deliberate series of marks on a portable object, created by people capable of complex material and symbolic behavior. Microscopic study of the Border Cave bone suggests that the 29 notches were not all produced in one uninterrupted action. Differences among the grooves indicate multiple marking episodes and possibly different tools. That pattern is compatible with information being added on separate occasions. A person may have returned to the bone whenever an event occurred, extending the sequence over time. Yet the event itself remains unknown. The marks might relate to days, objects, activities, social information, or something entirely different. The artifact matters because it demonstrates repeated inscription. It does not allow modern observers to recover the original count, category, or intention with confidence. Another famous object was found near the headwaters of the Nile in what is now the Democratic Republic of the Congo. The Ishango bone, dating to roughly 20 to 25,000 years ago, carries groups of notches arranged in 3 columns. A sharp piece of quartz was attached to one end, suggesting that the object may also have functioned as a tool. The notches are not distributed as one simple line. They form visible clusters with different totals, inviting attempts to discover an underlying pattern. This organization makes Ishango one of the most discussed artifacts in the history of prehistoric counting. Researchers have proposed many interpretations of the Ishango groups. Some have noticed quantities resembling doubles and halves. Others have emphasized numbers close to 10 or 20. A famous interpretation identifies prime numbers between 10 and 20. Another proposes a lunar calendar or a system based on 12. These readings are imaginative, but the same arrangement can support more than one pattern. Humans are extremely good at finding structure, especially when they already know what they hope to see. Ishango may preserve numerical reasoning, practical tool use, or another organized activity. Its importance lies in the structured marks, not in any single mathematical solution imposed upon them. Les Pradelles, Border Cave, and Ishango come from different regions, populations, and periods. None preserves a spoken number word or an explanation of its signs. Together, however, they suggest that ancient humans and perhaps Neanderthals repeatedly placed ordered information onto durable objects. That ability is a crucial bridge between memory and notation. Once a sequence can survive outside the brain, it can be checked, extended, carried, and possibly understood by others. These artifacts do not reveal one birthplace for counting. Instead, they point toward a long experimental process in which marks gradually acquired stable meanings within particular communities. What pressures encouraged people to count more precisely? Food had to be divided among group members. Tools and hunting equipment had to be prepared before journeys. Repeated visits to a resource might need to be remembered. Days between seasonal events could matter. Exchanges between communities could create obligations that lasted beyond one meeting. None of these activities automatically requires a formal number system, and archaeologists cannot assign a purpose to every marked object. But as tasks became more coordinated, exact quantities became increasingly useful. Counting offered a way to reduce uncertainty, compare contributions, detect shortages, and organize activities involving people, objects, and time. Material possessions may have increased that pressure. A mobile group with few durable objects can often manage through direct observation, memory, and social familiarity. A community storing many tools, ornaments, containers, food supplies, or exchange goods faces a different problem. More objects create more categories, and more categories create more opportunities for confusion. Comparative anthropological research has suggested a relationship between material complexity and the range of number systems, although it cannot reconstruct a universal path. The broader principle is convincing. As societies need to track more things, they benefit from methods that extend counting beyond small quantities and beyond the memory of a single person. Farming and animal management greatly expanded the scale of that challenge. Seed had to be reserved for planting. Grain entered and left storage. Animals were born, transferred, lost, or slaughtered. Workers contributed different amounts of labor. Food supported households, ceremonies, construction, and trade. A rough impression of more or less was no longer enough for every decision. Communities needed records that could survive across seasons and be inspected by people who had not witnessed the original transaction. This did not instantly produce written mathematics. It created an environment in which counters, measured containers, seals, tallies, and agreed numerical conventions became increasingly valuable. Across the Neolithic Near East, people began using small clay tokens in many shapes. Cones, spheres, discs, and other forms could represent particular kinds or quantities of goods within an administrative system. The precise meanings changed across time and place, so no single dictionary applies to every token. Their importance comes from their material structure. Unlike an ordinary pebble, a shaped token could distinguish one category from another. Several tokens could be gathered, separated, or checked. Quantity and type were now represented by deliberately manufactured objects. Counting had moved from temporary gestures and natural counters toward standardized tools designed for record keeping. During the 4th millennium BCE, some communities in Mesopotamia, Iran, and Syria sealed groups of tokens inside hollow clay envelopes called bulle. A seal impressed on the surface could identify the people or institution involved. Some envelopes also carried impressions corresponding to the tokens hidden inside, allowing the contents to be checked without immediately breaking the container. The bulla turned a group of counters into a protected record. It could travel with goods or preserve evidence of an agreement. This system shows that counting had become part of administration, where trust depended not only on personal memory, but also on objects that could be inspected by others. A much later example from Nutzi reveals the principle with unusual clarity. A clay container held 49 small counters, while an accompanying written record referred to 49 sheep. Here, the relationship between marker and animal is not merely imagined by modern observers. The written context confirms a one-to-one administrative correspondence. The example comes long after the earliest Near Eastern tokens, so it cannot explain the original meaning of every earlier counter. It demonstrates the durability of the underlying idea. One physical object can stand for one animal, and a sealed collection of objects can preserve an exact total independently of the herd itself. Denise Schmant-Besserat proposed that impressions made by tokens on clay helped give rise to the earliest written signs used for accounting. Once the outside of a bulla displayed the necessary information, sealing physical counters inside became less useful. Marks on flat tablets could perform the same administrative task more efficiently. This influential theory explains important similarities between some token shapes, impressions, and early signs. Archaeologists continue to debate how direct and universal the transition really was. Writing probably emerged through several interacting practices rather than one simple replacement. Even so, early written numerals clearly grew within a world already experienced in counting, sealing, measuring, and recording goods. Mesopotamian scribes eventually developed a powerful system organized around 60. In its mature Babylonian form, the value of a sign depended partly on its position, allowing a limited set of marks to represent extremely large or small quantities. The system supported accounting, geometry, astronomy, and calculation. One popular explanation connects 60 with the body. The thumb can count 12 finger joints on one hand, while the 5 fingers of the other track groups of 12. This method produces 60 elegantly, but its role in the historical origin of the system remains uncertain. What is certain is that positional notation transformed written marks into a flexible computational technology. Ancient Egypt followed a different path. Egyptian hieroglyphic numerals were organized around powers of 10, with distinct signs for 1, 10, 100, 1000, and larger values. Quantities were formed by repeating the required signs, making the system decimal but not positional. A sign kept the same value wherever it appeared. For faster administrative writing, Egyptian scribes used hieratic numerals, whose cursive forms could express common multiples more compactly. The result looked very different from Babylonian notation, even though both systems served taxation, construction, storage, and redistribution. Civilizations did not discover one inevitable way to write numbers. They designed systems around local practices. Other societies created still more solutions. Early Chinese writing used structured decimal numerals on durable surfaces. In the Andes, Qipu recorded quantities through the position, type, and grouping of knots on suspended cords. Maya scribes used dots for units, bars for groups of 5, and a shell-like sign for 0 within a largely base 20 system. These traditions arose in different environments and answered different social needs. Together, they reveal the deeper invention behind every numeral. Humans learned to place quantity into material form. Numbers began as relationships among objects, gestures, sounds, and marks. Eventually, those relationships became tools powerful enough to describe time, trade, architecture, and the universe.